Welcome to section 4.6. So as we get to the end of this chapter 4, talking about vector spaces, we're going to add a new concept called rank. Now rank is a numerical value that's associated with a matrix, and I'll explain what that is. So I'll introduce rank, and then actually I'm going to come back to the inverse matrix theorem. Remember we first dealt with that when we first did inverse matrices. It's all the properties that inverse matrices have, invertible matrices. And it's a really long list of equivalent statements, and now rank is going to play a part of that. So let's talk about what is rank. Well, rank, denoted rank A, not RA, rank A, is the dimension of the column space of A. Well, remember the column space was the number of pivots. So we can also think of this, and the number of pivots is also the dimension of the row space. So that's kind of nice. Now, I'm going to be 100% honest. This is what your book says. In general mathematics, rank has a little bit more involved into it. Specifically, that same exact rank that is equal to that is sometimes called the factor rank. That means the smallest number, k, such that A can be written as the matrices B and M, where B times M is equal to A. So B is M by K, and M is K by N. So it's the smallest number. Now that's a really hard thing to do, is to minimize this. So it's interesting enough that it comes out to be equal to the number of pivots. And there's a little bit more math that's pretty much behind that, and it's pretty cool. But I know many of you who are engineers don't really care about it, so I'm not going to spend a whole lot of time. Unless you want to ask questions, then I'll be glad to go into it, because that actually does have applications to minimization and other technology problems that we've dealt with, because there's other kinds of ranks out there, like Boolean rank of a matrix, which is actually very applicable to network analysis and so forth. All right, so the dimension of the null space is called the nullity. So we've already mentioned the dimension, how the last section, section 4.5, we mentioned how to find this. So the number of the null space is the number of free variables, and the rank, which is the dimension of the column space, is the number of pivots. Well, there's some other cool theorem that we actually get based on this thing. That if you go back to the last one, so in the last section, you can rewind and look at this theorem, we had a 3x5 matrix. That 3x5 matrix, remember, because you had number of pivots, number of free variables, take every single column. Thus, the rank of A plus the nullity of A is equal to n, the number of columns. The rank of A plus the dimension of the left null space is m, the number of rows. So we can actually leverage that if we just know these numbers, because we already know the size of the matrix. If we already know the rank, then I already know the size of the nullity, or the left nullity, as it sometimes is also called for the other one. So if I have a 7x9 matrix that has a two-dimensional null space, what is the rank? Well, very simply, we know that rank A is equal to the rank of A plus 2 is equal to 9, which, using simple arithmetic, the rank of A is 7. All right, that's super nice, super easy. Now, if I have a 6x9 matrix, can this matrix have a two-dimensional null space? The answer to that is, if it has a two-dimensional null space, then it would have rank 7. That's by our theorem that we just did. But if it has rank 7, notice that means there are 7 pivots. But 7 pivots would kind of be a problem, because how would you have because that's actually impossible for all the columns, because there's 9 columns, but 6 rows. Since the number of rows is less than the number of pivots that we're saying, that's completely impossible, so we have a slight problem. So this is using those theorems that we've already had to understand and realize, oops, this is not possible, and we can move on. The last one, by the way, this 7x9, that's completely possible. It actually means there's a pivot in every single row, but since the number of columns is more than the rows, we had 2 free variables. All right, so that's just a very simple way to look at this. So rank 7 is not possible in this 6x9 matrix. So rank is always, notice, you can always look at these two things. The rank, let me turn that on. The rank is always going to be less than or equal to both of those. It could be equal, but this can be no more than the smallest of those 2 dimensions. All right, so now the cool part is we can now apply this to our inverse matrix theorem we already had. Before, we added all this. Remember, matrix is invertible, square matrix is invertible, if first and foremost, if we could row reduce it to I, which also means that there were n pivots. It also meant that there was only the trivial solution to the homogeneous equation. It also meant that the columns were linearly independent. It also meant the linear transformation was 1-to-1. It also meant that, so all these things we already did, including the determinant is not equal to 0. Well, let's take what we now have and add on to that. We also mentioned that the columns of A form a basis of Rn. Well, that means actually that the column space is Rn, because that means it spans all of Rn. It also means that the dimension of the column space is n, but by definition, that means the rank is equal to n. So if the rank of a matrix, if it's a square matrix, and the rank is equal to the number of columns or rows, which are equivalent, then it's invertible. It also means the null space is just the 0 vector. I'm going to come back. Number 17 is actually the same thing. Is actually the same thing as saying number 4 right here. Number 4 is the same thing as number 17. So let me get that. They're really just saying the same thing. And one's referring to it as a homogeneous equation. The other one's referring to it in terms of null space. So again, same thing, written differently. And the dimension of the null space then is 0. So this put all together, we've now added up to 18 things in the inverse matrix theorem. But if you look at them carefully, you notice that most of these are very much the same. And again, we leverage them for different purposes depending on what we're doing. So all of them should mean the same thing because they're equivalent statements, but each one has its own benefit depending on what we're trying to show or how we're trying to apply it in actual situations. So just understand these and keep these in mind because this is probably the most powerful matrix that we use over and over again. All right, I hope that helps. Let me know what questions you have. Good luck.